Let's look at linear second order ordinary differential equations. So we have type 1. We have type 1. This one takes the form of a, the squared, the x squared, plus b, the y, the x, plus c of y equals to 0, where a, b, and c are a constant. But we want to look at two cases. If a equals to 0, remember, if a is equal to 0, it reduces, this differential equation reduces to only this one. It reduces to only this part because this one will be 0. So if a is equal to 0, we shall have b, the y, the x, plus cy equals to 0. Solving this one, it is separable, or we know that. So we shall have our b, the y, the x, I'm separating, equals negative cy, like that. What's next? The next thing is we shall have to separate and integrate. We separate and integrate. The y will come this way, we divide by y, then b goes the other side. We shall have negative c over b, then y comes this way. So we shall have a 1 over y divided by y, and the y, the dx will multiply the other side, and here we are remaining with c over b, but the what? The x. So when we integrate this, we are using separating variables here. We shall have, we know that integral of that is in ln of y equals to c over b, it's negative times x plus a constant, because this is a constant. Integrating it, we shall have that. So when we introduce exponential on both sides, we shall have y being equal to a exponential of negative c over b of x plus a constant, and this implies that y is equal to e of negative c over b of x dot, or multiplying it by exponential to power that, and therefore our y will be equal to a, that's any constant, of exponential negative c over bx. But let us say, let our m to be negative c over b. For uniformity, our y will be equal to a constant a into exponential of mx, because this part we have related it to be what? M. Now what does it imply? This is the solution. If the DE, this is the solution, is a solution if the differential equation, for the differential equation where a equals to 0. But what if when a is not equal to what? To 0. When a is not equal to 0, then it implies that we shall substitute the value of y into this differential equation. So what are we going to have when we are substituting? We shall have a, d squared, the x squared of a, this is our y, we are substituting in the y, the x, wherever there is a y, we want to put that. So we shall have a of exponential mx plus b d dx of a exponential mx plus c into a of exponential mx being equal to 0. So when you look at this thing, what's the common thing here? The common thing here is what? The common factor. That's the common factor. But before looking at the common factor, I want to differentiate, because the squared dx means we are differentiating this. So when we differentiate this, we shall have a small a and this big A, then we drop that one down, m will come down, but twice exponential of mx plus this part here shall have a b, then this a is also a constant, then we are differentiating this part, we drop down the m and remain with exponential m of x plus c of a, then we differentiate this, of which we shall have c of a to the exponential m of x, because we don't have any differentiation here, and this thing will give us a 0. So common factor, we look at the common factor at this point under this equation. Our common factor is a exponential of mx. That's our common factor. We pull it out, then we remain inside with am squared plus bm plus c equals to 0. But we know that a to exponential of mx is not equal to 0. When you get your calculator and you put exponential to n of anything, power anything, it will not give you 0. It will never give you 0. So since this part is not equal to 0, the exponential of 0 is not equal to 0, what does it imply? So this implies that the only portion that brings a 0 is am squared plus bm plus c equals to 0. And this is a homogeneous what? This is a homogeneous differential equation. That's our homogeneous differential equation. So when we are solving a homogeneous differential equation, I'm trying to mean when our m, this m is in form of the y, the x. For example, if we have a m squared plus b m plus a c being equal to 0, and this m equals to dy dx, this implies that m dy squared dx squared plus b dy dx plus c of y equals to 0. We can solve this because this is a quadratic equation. So when we are solving, this is in form of a quadratic equation. It is in the form of this, a differential equation, but in the form of a quadratic equation. This one is called auxiliary equation. It is called auxiliary equation. So when we are going to solve such a homogeneous equation like this one, we have 3 cases. So we want to look at those cases. Case 1 we look at if b squared is greater than 4ac. What does it imply? It implies that the factor of this equation that is equal to 0, the factors when you solve this equation that you obtain from this differential equation, it means that the factors are real and distinct, not the same. Factors are real and not the same. That's when b squared is greater than 4ac. So if you get, let's see, 1 and 2, these are real factors but different, they are distinct. What does it imply? How do you solve such? How do you get the complementary solution of such a differential equation? Our complementary solution of such equation will be equal to any constant, say a, raised to exponential m1 of x plus a b exponential of m2 of x. What am I trying to say? If you solve this quadratic equation, or say the characteristic equation, and you get 1 and 2, your complementary solution for that differential equation will be any constant a raised to 1, our m, the first factor, times x, then b, bring another factor, which is m2, which is going to be 2 of x. Your complementary solution will look like that. So this was case 1. We want to look at case 2. Case 2, if the b squared is equal to 4ac, this implies that the factors are the same and equal. They are equal, real, equal, and the same. For example, you can solve this auxiliary equation and you have a 2, and a 2. How will your complementary solution for that differential equation look like? Our complementary solution will be in a form of exponential m of x, exponential to the power of exponential of mx into, have a bracket, a of x, any constant, you can use any constant here, plus another constant, ax plus b, you can give another constant. This means that this 2, we take only 2 of it, you take only one factor, is this m. So if it is 2, then our complementary solution will be exponential of 2x into ax plus b. This is when your auxiliary equation gives you the same factor, which are equal. Case 3. In case 3, we look at the case where b squared is now less than 4ac. What does it imply here? It implies that you will have the roots which are in form of a complex number. In the form of a complex, they are complex. For example, your root will be in the form of alpha plus or minus I beta, like that. For example, you may have m being equal to 1 plus or minus 2 of I, like that. This implies that this is your alpha and this 2 is your beta. How will the solution for such a differential equation will look like when the auxiliary equation of the differential equation gives you a complex? It will be in the form YC. The complementary solution will be in the form of exponential alpha x into a, and a constant, say a, cos b of x, this is beta, cos beta of x, plus b sine beta of x. This is how your solution will be. For example, if you have a 2 as our beta, then our complementary solution will be in the form of, our alpha is now 1, so we shall have exponential of alpha, our alpha is 1 here, of x into a, cos, what is beta? Our beta is 2, cos 2 of x plus b sine 2 of x. This is the complementary solution for such a differential equation giving you a complex roots. Thank you for watching. Watch my next lecture. I'm going to give examples about homogeneous differential equation. Thank you. Please subscribe.